In this video, we are going to look at factor theorem. Factor theorem says that x minus b is a factor of a polynomial p at x if and only if, so this if with the extra f means if and only if, p at b is equal to 0. Similarly, ax minus b is a factor of a polynomial p at x if and only if p at b over a is equal to 0. Recall from previous videos that if we had a factor of a polynomial, that its remainder was 0. So this is what this theorem is telling us, is that we will have a factor of our polynomial if the remainder is equal to 0. To test then whether a binomial is actually a factor of a polynomial, what we want to do is sub in our factor and see if our remainder is 0. For this example then, we're going to plug in f at 2 into our polynomial. We would have 2 cubed minus 7 times 2 squared plus 9 times 2 plus 2 gives us 8 minus 28 plus 18 plus 2, and if we solve that, would give us 0. Now, because we've got a 0, this means that x minus 2 is a factor of our polynomial. Our second example then asks us to find a factor of this polynomial x cubed plus 8x squared plus 19x plus 12. What you want to do to figure this out is you're going to take your last number and look for factors of 12. Possibilities could be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and plus or minus 6. Now, so these are all possible b values that we could potentially test for. Since this polynomial is positive, it would be a good idea to try some negative values for b. What you want to do, unfortunately this is a little bit of a checking game, is you want to try some of your negative values. Let's try negative 1 first. If we plug in f at negative 1, we get negative 1 cubed minus 8 times negative 1 squared plus 19 times negative 1 plus 12. We would have then negative 1 minus 8 minus 19 plus 12, and this, in fact, does give us 0. That means that x plus 1 is a factor of this polynomial. If we did not get a remainder of 0, then you would want to go on and maybe try negative 2. If that didn't give you 0, go on and try negative 3. And you have to just keep going until you find one that will actually give you a 0. The possible values of b are factors of the constant term if the leading coefficient is 1. In this example, the leading coefficient was 1, so doing it this way is the appropriate manner. To find other factors, at most 3, since p at x is cubic, we could either use the remainder theorem, which is time-consuming, or we could do long division. Let's do our long division then. So we know x plus 1 is a factor. We're dividing our polynomial x cubed plus 8x squared plus 19x plus 12. X goes into x cubed, x squared times. Multiplying them out, we got x cubed plus x squared. Subtracting these two sets of terms, 8x squared minus x squared gives us 7x squared. Bring down our next term. X goes into 7x squared. 7x times x is 7x squared. 7x times 1 is 7x. 19 minus 7 gives us 12x, and we'll bring down our 12. So x goes into 12x 12 times, and then the rest of this should work out if you've done your theorem correctly to give you a remainder of 0. That means that x cubed plus 8x squared plus 19x plus 12 is equal to x plus 1 times x squared plus 7x plus 12. Now that we've done this, we could factor this as well if we wanted to factor our entire polynomial. And it's pretty easy to factor that. A good rule of thumb is that what you want to do is check and see if you can factor by common factoring or grouping first, because this is much faster to do than long division. Long division takes us quite a bit of time. For example, this one here, x cubed plus 2x squared minus x minus 2, we can factor simply by grouping. If we factor out a x squared in the first two terms, we'd be left with x plus 2. If we factor out a negative 1 with our next two terms, we'd be left with x plus 2. And then this would factor to x plus 2 times x squared minus 1. And x squared minus 1 is a difference of squares. Factor all the way down to x plus 2, x plus 1 times x minus 1. And you see how fast that is, and we didn't even need to do long division. What do we do then when our leading coefficient is not 1? In this example, our leading coefficient is 5. In order to find factors then to test to see what would be a factor of this polynomial, we have to use the rational zero theorem, which basically says that if p at x is a polynomial with an integer coefficient and x equals b over a is a zero of p at x, so that means x equals b over a is a factor of p at x, a and b are integers, a cannot equal 0, then b is going to be a factor of the constant term, so this would be our b here. A is a factor of our leading coefficient, then ax minus b is a factor of p at x. Okay, I know this is a whole bunch of jumble of words, but let me show you what this means. What we want to do is we want to look for factors of our a term. So our a term is our leading coefficient. Possible a values then are going to be factors of our leading coefficient. And for this one, it's just going to be plus or minus 1 or plus or minus 5. Nothing else will divide into 5. We then want to look at our constant term and look for possible factors of that. So possible b values could be plus or minus 1, plus or minus 2, or plus or minus 4. And what this rational zeros theorem is saying is the factors we would want to test are values of b over a. So what you want to do is you want to do all the combinations of b over all the combinations of a. That means you could have plus or minus 1 over 1, that's these two, which is just plus or minus 1. You could have, if we take plus or minus 1 over 5, we'd have plus or minus 1 over 5. Looking at this second set of terms then, we'd have plus or minus 2 over 1, which is just 2, or plus or minus 2 over 5, or looking at this now, plus or minus 4 over 1, which is just 4, and plus or minus 4 over 5. So these are the values that you would need to test in order to find a factor for something that doesn't have a leading coefficient of 1.